So last class we started looking at nonlinear circuits. So the basic problem, okay, is that if you write down the KVL, KCL for a nonlinear, for a circuit containing nonlinear elements, and you want to, so those you can write it in some form, right, in terms of the voltages and currents, and those inherently look linear. However, the extra relationships that you use to actually solve for the voltages and currents in the circuit, okay, so those are the elemental relationships. Those could be nonlinear, okay, and very specifically we took the most one of the simplest nonlinear elements, which is a diode. Okay, this happens to be a two-terminal nonlinear element. Okay, and the expression relating the voltage and the current, the voltage across the diode and the current through the diode. Note the directions. Okay, so the current flows from the anode to the cathode, and the voltage is positive on the anode and negative on the cathode. Okay, with these current conventions, directions, okay, there is an exponential relationship. So the I is some constant Is times exponential V by Vt minus 1. And this Is is called the saturation current, sometimes also called the reverse saturation current, because as you can see, when V is very small, very large and negative, what happens is the current actually settles down, ends up being minus Is. Okay, this exponential V by Vt will just go to 0, you will just get minus Is. So sometimes Is is also called the reverse saturation current. When V is greater than 0, okay, you will see it of course, number one, it passes through the origin. Okay, when V is 0, I also happens to be 0. Do you expect this? Do you expect it to pass through the origin? Well, the basic idea is that at least as far as the diode is concerned, it happens to be a passive device. Okay, if you have a passive device, it can only operate in these two quadrants. Do you see why that is? Do you know why that is? Because V times I has to be positive. Okay, for a passive device, based on the convention that we have chosen, V times I has to be positive. Take the case of a resistor. Okay, you choose a certain reference direction V and a reference direction I. Okay, the resistor always consumes power, which is positive by our convention. Okay, therefore the resistor operates only in the first and third quadrants. What is the characteristic of a resistor? The characteristic of a resistor is a straight line occupying only the first and third quadrants. Okay, so any two-terminal passive element should occupy only one of these two quadrants. Okay, now there are cases where you might have a diode, for example, which might occupy the one of these two quadrants. Any idea where these might be used or where they might occur? Well, as it so happens, if you pick up a solar cell, right? Of course, you have energy coming in the form of light. Okay, but it will occupy a different quadrant. Okay, it won't be only, it will be in the fourth quadrant. Okay, it won't occupy the first or third quadrants only. However, okay, basically what happens is when you shine light on it, okay, it will occupy the fourth quadrant, but over a very small range of voltages and currents. Okay, it won't completely be in the fourth quadrant, in a certain region of operation. Okay, but anyways, coming back to our goal here is to figure out what happens to the diode. So if you see, if you pick up values very large and positive, let us say V was very large. Let us say, what do you mean by very large is actually fairly vague, right? Let's face it. So when I say very large, what I mean is much larger than Vt. Vt is the thermal voltage, which is kT by Q, right? And if V is much larger than Vt, let us say, okay, let us say 4 or 5 times, right? Then what happens is this exponential term in the previous, in this relationship, this term becomes much larger than 1, right? What is, if V is equal to Vt, this happens to be E, which is 2.7, right? If it is twice Vt, it becomes E squared, okay? And you can clearly see when V becomes some 4 times Vt, this blows up to a large enough value such that you can neglect that one term. Okay, what is Vt? Vt is kT by Q. If you calculate it at room temperature, what did it turn out to be? This is around 25 millivolts. So in other words, if V, the voltage across the diode, is larger than, let's say, 100 or 120 millivolts, okay, you can make the approximation that it's simply an exponential and does not have e power V by Vt minus 1. Is that okay? And of course, Vt is kT by Q. You know, I already explained last class. K is Boltzmann's constant, T is absolute temperature, Q is the electronic charge. Okay, so now our next step is to use the diode in a very, very simple circuit and try to understand how it operates. The simplest circuit which we started looking at was just a voltage source with a resistor and the diode in place of the nonlinear element. You can write down, you know, the relationship, element relationship, as well as the KVL, as well as KVL, KCL. Okay, but unfortunately, there is no other go than to solve the nonlinear equation to get the solution. Okay, if you have a nonlinear element, there is no other way than to solve the nonlinear equation. Okay, we don't have any way out of that. There are many ways to do this using simulation. Okay, if you want to do it by hand, you can try some kind of iteration. Newton-Raphson method can also be done by hand. You can try some kind of iteration. Okay, you can try it graphically, which is what we did in class last time. Okay, there are many ways to solve this network. But our goal is to go one step further. Okay, suppose you have solved the nonlinear equation once. Okay, question is, can you use it to do something else? Okay, something further. So that is, we are going to look at that in today's class. But let us go back to this graphical method. So you plot the equation of the diode, I equals f of v. Okay, then you can also plot the IV characteristic of the resistor, okay, which is in series with the diode, and that goes here. And of course, because these two are in series, the intersection point will give you the this is the equation of the straight line describing the other KVL relationship. I'm sorry, the resistor and the diode, you'll draw it in a different way. But this is the straight line here, okay, represents the KVL equation around the loop, and the intersection point will actually give you what the solution is, because the two equations describing this are the elemental relationship and the KVL equation. Is that clear? Any questions? Okay, now let me call that intersection point V0, I0. Now I want to figure out what will happen if I had applied a different voltage. Okay, I am calling that different voltage some Vs plus delta Vs. I want to find out what will happen to the circuit, what will be the new solution for the voltages and currents. Right, this is what I mean by extending it further. Okay, first what did we do? We figured out how to find out the solution, and there is no other way than to solve the nonlinear equations. Now I want to go one step further. So let us say I found the solution when I apply 5 volts, okay, and this resistance is some, let us say 1 kilo ohm, and I found out what the current is and what the voltage is. Now suppose I want to find out what will happen if I apply a voltage different than 5 volts, different from 5 volts. Suppose I told you I am applying 10 volts. How do you figure out what will happen? So the most important thing to remember is that the minute you have a nonlinear element, the circuit, you can no longer apply superposition. Okay, so just because you have applied twice the input voltage, the voltage of interest will not be twice, it will be something else. Okay, that's number one. So you can't do that. And in fact, if you actually apply a totally different voltage, okay, which is very different from the original voltage, you have no choice but to solve the nonlinear equations once more. Okay, there is no other way to do it. However, suppose I had told you instead of applying 10 volts, I had told you you are actually applying 5.001 volts, right? We want to find out what will happen. Can we actually do this? Find out what will happen in a very simple way, without solving the nonlinear equations again. That is the whole point. The reason is very simple. Okay, if you want to solve a linear network, you write down the set of voltages and currents, right? The relationships using KVL, KCL, elemental relationships. You can write it in matrix form, invert the matrix, get it very easily through simulation. It's very fast also. Okay, if you need to solve the nonlinear equations, it's much slower. Even in simulation, it's significantly slower than solving a set of linear equations. Okay, that is the reason why you want to figure out how to make this circuit simpler. Okay, both for hand calculations as well as for simulations. So let us say this original set of V0, I0, okay, we are going to call that the operating point. Okay, and we are going to see what will happen if I apply a voltage which will cause the operating point to deviate by a very small amount. Okay, in other words, I am going to apply a voltage which I am going to call delta Vs, and delta Vs should be very small. Okay, we will see what this very small means in a little bit, but it means this should be very small. And if I apply a small enough delta Vs, I can say the current is going to change to from I to I plus delta I. The voltage across the diode will change from V to V plus delta V. Okay, we are good so far? So in reality, if I want to find out the new operating point, okay, I need to draw this. Okay, I need to draw this new line with x-intercept Vs plus delta Vs. Okay, y-intercept is Vs plus delta Vs by R1. Okay, and I find out where it intersects the diode curve. Okay, and I can find out. That is a graphical way of solving it. But suppose this delta Vs was very small, so these two lines are going to be very close to each other. Okay, the change in operating point went from V0, I0 to V0 prime, I0 prime. What are V0 prime, I0 prime? Some V0 plus delta V, comma, I0 plus delta I. That is what these two what this new operating point is. Is that clear so far? Okay. Then what I am going to do, I know that the device behavior is non-linear, but if I choose a small enough shift, okay, I can replace this non-linear behavior by a straight line. Okay, how am I doing that? I know that any function can be represented as using the Taylor series, okay, as expanded in terms of its derivatives at a particular point, right? And if I choose a small enough deviation, okay, I can discard the higher order terms of the Taylor series and use only the first order term. It is an approximation, okay, but at the end of the day, in most of these cases, you are interested in the best possible approximation. You may not be 100% accurate with the value, but you will get an extremely accurate result if you choose a small enough delta Vs. Is that clear? How do you figure out if your approximation is correct or wrong? You will have to go back, right? You can always go back and plug in and figure out what the value of the higher order terms of the Taylor series are, okay, if they are negligible compared to the first order term. If they are negligible, you are good to go. Okay, so suppose I can replace it by the Taylor series. What I am going to do is I am going to take this behavior around V0, I0 and I am replacing it by a tangent, okay, by the tangent at that point, okay. The minute I replace it with a tangent, I can, to make things easier for myself, I am going to shift the coordinate system, okay, from this point to V0, I0. Okay, And if I do that, okay, I'm shifting it from here to here, and in fact, instead of calling it V prime I prime, I can actually call it delta V and delta I. Okay, the new axes are delta V and delta I axes. Okay, and along the delta V delta I axis, what do I have? I actually have the relationship between delta I and delta V for the diode. Okay, since I have replaced the diode with the Taylor series approximation, it is a linear relationship. Okay, it is a linear relationship. Okay, the new values are of the straight line describing the other KVL equation. Okay, now that I have moved the axis, that is the y-intercept is delta Vs by R1, the x-intercept is delta Vs, and now you can see we have completely shifted. Okay, we have completely shifted from dealing with V, I, V naught, I naught to only delta V and delta I, delta Vs, and so on. I hope you all see this. If you want me to explain it again, I can. Did everybody understand that? What is the whole point of doing this? You solve the operating point, that is the original point, okay, V naught comma I naught. You solve for that using the nonlinear relationship. The next step is to move your coordinate axis to V naught comma I naught. Then you replace the characteristics of the nonlinear element by the tangent at V naught I naught, okay, which happens to be the derivative at that point. Okay, derivative at that point. If you choose a new operating point, okay, the straight line will change. That is the first thing you need to understand. Okay. Right? I hope you all see that. If I had chosen this as the new point, the slope will change at that point. Okay. So in other words, the straight line describing the relationship between delta V and delta I will also change. Okay. So calculating the operating point is extremely important. Now once you have done that, what are you going to do? This straight line that you have just replaced it with is actually looks like a resistance, right? Looks like the characteristic of a resistance, except you are dealing only with incremental quantities. So now I can replace the circuit, okay, by what is called as incremental equivalent circuit. Okay. This is what is called the incremental equivalent circuit. Okay. What happens to the voltage source? The value of the voltage source is delta Vs. The value of the resistance stays the same, R1. The value of the diode is replaced with a resistance Rd, and Rd is nothing but 1 over f prime of V at V naught. Is that clear? How do you know it's just a resistor, and how do you know the circuit looks exactly like this? Well, it's very simple. What you do is actually try to correlate what kind of circuit would actually give you this kind of characteristic. For what kind of circuit would you actually try to find out the intersection between a straight line like this and a straight line like that? You compare it with what you did in the diode. It's pretty obvious that it has to be a single loop network like this, which is what you considered with the diode, except now you're dealing with delta V, okay, because the axes are delta V, delta I, and you can see that the y-intercept is delta Vs by R1, x-intercept is delta Vs, which represents a delta Vs voltage source and a resistance R1. So the value of the resistance R1 stays the same. The diode, however, is replaced by a resistance of value Rd, which is 1 over f prime of V at V0. Okay? So let us do a quick example. Okay, to tell you how you will solve this problem. So let us say this is 5 kilo ohms. Okay, and I'm going to say 5.69 volts, but let us see. What do you do about the diode? You need to know what the saturation current of the diode is. Okay, you need to know anything else? Huh? Thermal voltage, you need to know the temperature. Exactly. Okay, if you are not given anything else, you just assume it's 300 Kelvin. If you are not told anything else, you assume it's room temperature, which by convention is 300 Kelvin. Okay, so let us say it is some 10 power minus 15 amperes, and I'll say T is 300 Kelvin. Okay, now I need to figure out how to solve this. You can put in the equation. Can somebody find out using a calculator? It should be very simple. What the voltage would be? Can you find it out using a calculator? You will have to iterate even if you use a calculator. So what I'll do is, to make things faster, I'll give you a small table. Okay, I versus V for the diode. It is just something which I drew up using a calculator for a few values. Okay, I'll say 100 microamps, 1 milliamp and 10 milliamps. Okay, and I think the values were, yes, 630 millivolts, 690 millivolts and 750 millivolts. Okay, what do you think the voltage and currents are? Sorry. What do you think the voltages and currents are? What are I and V? What is I? Well, yeah, it's clear that, okay, this is 0.69 volts. Okay, so if you had applied 5.69, okay, you'll get 0.5, you'll get 5 minus 5.69 minus 0.69, which is 5 volts across this. 5 volts across the resistor. 5 volts by 5 kilo ohms is 1 milliamp. Okay, very clearly this is the operating point, right? This is just a, obviously you would never ever do it this way. Okay, you would need to have an infinite number of values if you really want to get good accuracy, right? But that's not the point. I just give you this table to move on quickly. If you really need to do it, you will need to solve the equation, do some iteration. Okay, however, I will also tell you a simple way to solve it in just a minute. Okay, now it's very clear that this voltage is 0.69 and I is 1 milliamp. What do you do next? Suppose I want to find out what will happen if I applied a delta Vs. Okay, all these currents and voltages will change. Okay, I want to find out the behavior of the circuit. What do I need to do then? I need to figure out Rd, correct? I need to figure out RD. So this is is exponential V by Vt minus 1. Okay, and there are two things I know. I naught is is exponential V naught by Vt minus 1. This is the operating point of the diode. It has to be, this equation has to be satisfied, right? V naught comma I naught is the operating point of the diode. This equation has to be satisfied. I hope all of you see that. Does everybody see this? Okay. Now what I need to do, I need to figure out what RD is. What is f prime of V? It's Is by Vt exponential V by Vt, right? Now if I want to find out RD, okay, RD is nothing but 1 over f prime at V naught. What is this? Vt by Is exponential V naught by Vt. And what is this? I'll say this is approximately Vt by I naught. The reason is very simple. Okay, I told you if V by Vt was much larger than 1, even at least 4 or 5, okay, the one term can be neglected. This one term can be neglected. Okay, and you could say this is okay, Is exponential V naught by Vt. Okay, which means the diode resistance is nothing but Vt by I naught. This is quite simple, right? It does not depend on anything else. Okay, the diode resistance depends only on the thermal voltage, which is just a function of the temperature at which you are operating, and the current flowing through the diode. Okay, this is the operating point current flowing through the diode. In our particular example, what is RD? Okay, so I'll say, to make things, I'll say RD is Vt is 25 millivolts by 1 milliamp, 25 ohms. Okay. Which means my circuit now is a very simple incremental equivalent circuit. I have delta Vs. Okay, I have a 5 kilo ohm resistor and I have a 25 ohm resistor. Now what I can do, I apply any delta Vs I want to. I can find out delta V and delta I very easily. This is delta I. What is delta I? Is nothing but delta Vs by 5.025 kilo ohms. Right? That is delta I. Delta V, okay, is nothing but delta I times 25. Correct? So whatever delta Vs I apply, I can find out delta I and delta V. Now you can just extend this to a much larger circuit. Okay, this is the simplest possible circuit you can think of using having a single diode. But suppose I have a circuit with 20 diodes. You have to solve the nonlinear relationship between the voltages and currents, okay, to establish the operating point. But the minute you establish the operating point, okay, for any other small change in the applied source voltages or currents, okay, you basically you can draw the incremental equivalent circuit, okay, and figure out what will happen to the increments across any element in the circuit using just a linear system of equations. That is the power of this incremental, what is called incremental analysis or small signal analysis. Okay, this is also called small signal analysis. Okay, and you'll see in later courses why it is called small signal analysis. I hope the incremental portion is clear. So if I were to write down the steps, okay, that you would go through, okay, to with the incremental circuit, how would you build an incremental circuit? Okay, how would you build the incremental circuit? Of course, I am already taking for granted that you have already calculated the operating points V0, I0 for all elements. Okay, that should be known first. But once you know that, you want to draw the incremental circuit. What do you think the incremental circuit will look like? Number one, okay, you can say that it will have the same graph as the original network. You have not changed the graph of the network. Okay, you are just trying to replace each element by its some conductance, which is f prime v. Okay, so the incremental circuit has the same graph as the original circuit. What else can you say? Can you say anything about the branch voltages and currents? The branch voltages are all the incremental voltages. Okay, let us call them delta Vk. Okay, the branch currents are all the incremental branch currents delta Ik. Okay, and branch currents are delta Ik. What else? What happens to resistors? What happens to linear elements? They remain the same. Whether for linear elements, okay, if I take a resistor for example, whether if I apply V, I'll get I. Okay, if I apply delta V, I'll get delta I. Right? The relationship is the same, is linear whether you consider small changes or very large changes. Okay, so even if you take the incremental circuit, the linear elements will remain the same. What about independent sources? What will you do with independent sources? What did we do with Vs? We replaced it with its increment with some incremental equivalent, which is delta Vs. Okay, that is what you are applying from outside. Okay, now the excitation is no longer Vs, it is delta Vs. Okay, so you replace the voltage source with the voltage source, the current source with the current source, but the value is the value is nothing but the increment or change in the original value. What do you do with nonlinear elements? okay, nonlinear elements are replaced with linear resistors, okay, whose value is 1 over f prime of v, where f of v is I equal to f of v is the elemental relationship. R equals to 1 prime, R equals 1 by f prime of v, and for those nonlinear elements the delta v delta I relationship is now also linear. You can write delta vk as R times delta ik for these nonlinear elements in the incremental equivalent circuit. Is that clear? Good so far? Okay. Now, so this is easy now. So if I tell you, originally it was operating point was something, okay, let's say you are able to calculate that, and I tell you the source changes by 1%, right? Or whether it's a current source or a voltage source, if it changes by a very small percent, you can very easily figure out. If if you have 3 nodes or 4 nodes, you will take one as a reference node, solve for the incremental changes in the current, okay, add those increments back to the original operating point to get the total current, right? If if you get a delta, if original voltage was V and you get a delta V, V plus delta V is the total voltage. Is that clear? Now let us go back to this diode, because that is still a little bit troubling, right? I am sure it is. It must be for you people. It's an exponential relationship, right? If I have more than one diode in the circuit, it already seems like a big deal, right? How do you calculate the operating point? Any ideas? I'm sure you all agree that it's a big deal. We are easily able to do it for when you have one diode, right? You had one resistor, one diode, one voltage source. Okay, you can iterate and solve it. If I give you 3 loops with one diode in each, right, it's going to be extremely difficult to solve this. So how do you propose we handle that? Okay, so let us take a step back. I said you can iterate to find the solution. How do you know where to start the iteration? Will you start at 0, 0 or something? Or will you apply some random voltage? Or what would you do? So as it turns out, you go back to this table, okay? Do you see anything weird about this table? The current is changing by 2 orders of magnitude, okay? But the voltage is changing by very, very little, right? Current is changing, it's going from some value to 100 times its value. The voltage is changing by very, very small percentage, right? This is changing by around 120 millivolts, so 15% or something like that, okay, or 20% for a change in current of 2 orders of magnitude. Do you expect this? Of course, this is an exponential relationship. A very small change will actually give you a very large change in the output. Okay. So you can also see that these numbers are all clustered around this 600, 700 millivolt range. So a very good starting point, okay, is to approximate the diode relationship, okay, by a much easier characteristic, okay. This of course will only give you a crude solution, but if you see, in a majority of cases it will actually get you very close to the answer. Okay, what I'm doing is I'm replacing the exponential relationship with a kind of a straight line beyond a certain point. Okay, what I'm saying is if the diode is off, when there is no current, the voltage is sorry, when the voltage applied is less than 0.7 volts, the current is 0. Okay, but for any other current, the voltage will be 0.7 volts. Does that make sense? This will give you a very good approximate value. You will find an error. Obviously, the curve is going to go on like this. Okay. If you choose here, you would have chosen a slightly larger value than you should have. If you go the other side, you would have chosen a slightly smaller value than you should have. But what you will find is for a large range of currents, this approximation will be quite good. Okay. So very often, okay, for hand calculations, this is the characteristic that is used for the diode. To use this characteristic, do you need to know anything about the diode? Suppose I told you this was the characteristic of the diode, the green one. Do you need to know anything about the diode? Do you need to know the saturation current? No, you don't. We are just blindly replacing the diode with this. So the whole idea of this is to get a good estimate of the operating point. Okay, for example, how would you use this to solve a circuit? Suppose I told you this was 5 kilo ohms. I take a 5 kilo ohm resistor, put it in series with a 5.7 volt voltage source and complete the loop with the diode. How would you figure out I and V across the I through the diode and V across the diode? First you assume let's assume it's forward biased. Okay. If it was forward biased, there will be a voltage V and a current I. What is the voltage V? Is 0.7 volts. What is the voltage across the resistor then? It's 5.7 minus 0.7, which is 5 volts. What is the current? 1 milliampere. 5 volts by 5 kilo ohms. Imagine if I had given you a second loop. Okay? If I had tacked on a second loop like this, would you have been able to calculate the currents and voltages? Of course you can. You first assume that the diode is forward biased. Okay. You find out the solution and go back and ensure that the diode, check whether the diode is forward biased or not. You have to do that. Okay. You don't know if the diode is operating in this green region or in this yellow region. In the yellow region, you assume that the diode has zero current. Okay. In other words, if I had replaced the diode like this, okay, you can go back and check for yourself. You can start off by assuming this is forward biased, but it will not lead you to a consistent solution. The reason is very simple. Okay, this is 0.7, this is 0.7. What is the voltage across this resistor? 0. There is no current through the second diode, very clearly. Okay, there is no current through this diode. Okay, which means your original assumption was wrong. Okay, if you apply 0.7 volts, you have to get a current through the diode. You see how you can, so you will have many permutations and combinations. You can work out what will happen, what the solution to the circuit should be. Just from very simple KVL, KCL. Any questions so far? This is just a simple way. We do not expect you to solve the exponential equations in the exam, obviously, or even in the tutorials, unless we ask you to check something. Okay, this is not routinely expected for hand calculations. Before one day before the exam, I don't want a question about whether you'll be expected to solve. Obviously, in 50 minutes, if you are spending time solving equations with exponentials in them or doing iterations, it's not going to work out. Okay, if you want a more accurate solution, you do this. You will find out the states of the diodes, whether they are on or off. Okay, then you go back, you have assumed it's 0.7 volts, you find out the voltages and currents. Then you go back and do the iteration with these values. Now you have found out the current through the diode. Now if you know IS, you can go back, plug in IS, okay. You know this current is 1 milliamp, forget about the blue curve. So let me disconnect the, let me get rid of the blue one. Now that you have found out this current is 1 milliamp, and let us say this IS was actually 10 power minus 15 amperes, you go back in and plug, okay, that and find out the actual value of V. It will be slightly different from 0.7. Maybe it's 0.65, maybe it's 0.75. Right? What do? You can always keep doing this iteration to get more and more accurate values of V and I. But for hand calculations, you really don't need it. Okay? Because when you go to the next step, what are you going to do? You are going to find out the incremental resistance of this diode. Right? Whether you have 1 milliamperes or 0.99 milliamperes, the incremental resistance may change from 25 ohms to maybe 24 point something ohms. It will make a very, very small difference for your hand calculation. We don't care to that extent. If you really want the absolute to the 10th decimal place, you go stick it in a simulator. It will tell you. You can write a small program. Okay. One last thing before I close the class, because I want to finish it off because you need it for the tutorial. Suppose I have a nonlinear two-port. So far we have been looking at single elements whose relationship is nonlinear. Current voltage relationship is nonlinear. Suppose I take a two-port which consists of these nonlinear elements and maybe some other linear elements also, let us say, right? Maybe resistors and diodes to start off with, but it can be any nonlinear two-port. Can you do anything about this? You can extend the same thing which you did for the diode to this nonlinear two-port also. So V1, I1, V2, I2 are the equations, are the two-port voltages and currents. Suppose you have found out using your nonlinear relationships, you find out the operating point of the nonlinear two-port. What do I mean by the operating point? I have found out that these values are actually V10, I10, V20, I20. Okay? Now I am telling you, I want to find out the relationship if I have incremental voltages, okay, and incremental currents. How do you do this? If you had a one port, what did we do? An element is just a special case of a one port, nonlinear one port, right? If you have a nonlinear one port, the relationship was I equals f of v, you replace it by a resistor 1 over f prime. What do you think you would do here? As it so turns out, so you need to know now the relationships between these different elements. So let us say I1 was some f1 of v1 comma v2, I2 was f2 of v1 comma v2. Then you can write delta I1 as the partial derivative of f1 with respect to v1 at the operating point times delta v1 plus the partial derivative with respect to v2, dou f1 by dou v2 times delta v2. Similarly, delta I2 is dou f2 by dou v1 times delta v1 Okay, you can write the relationships between delta i's and delta v's in this form. What are these guys here? What is that? Yeah, you said the right answer. What is that? These are the incremental y parameters of the two-port network, nonlinear two-port. These 4 parameters here are the incremental y parameters of the two-port network. So I'll just write that here. Okay, so if you are given some arbitrary function relating I1, V1, I2, V2, okay, F1 and F2, you can find out you can linearize the nonlinear two-port, okay, and once you have done this, with respect to delta I1, delta I2, delta V1, delta V2, whatever you did for linear two-port will be valid as long as you are using only the increments. So in other words, I'll use small y's to represent incremental y parameters. Is that clear? What are these y parameters? They are basically resistances or conductances in parallel with controlled sources at the input and the output. You have a conductance small y11 in parallel with the controlled source, okay, y12 times V2 at the input. At the output you have y22 in parallel with y21 V1. You can do the same thing if you want to analyze it for the increments. Do not confuse the two. Now the tutorial has a few problems where you actually find out the y parameters of some of these two ports, some non-linear elements. Any ideas as to what kind of non-linear two ports you might be interested in? A transistor. Okay, it so happens it's a 3-terminal element. It's a 3-terminal two-port element, and for that you try to build the y parameters. Well, then after that you can apply any increment and you can find out what happens. Okay, so we'll stop here. 26th there is no class, Thursday. 27th there will be a tutorial, okay, and then after that from Monday we'll have classes. Monday is Friday's timetable, 8 o'clock for us, doesn't matter, 8 o'clock in the morning. Yes.
What do you think about when we...
Come to say. I think, yes.
When it is in reverse bias, like just we are taking the operating voltage of diode as 0.7 volt, that's why like this.
Yes. No. Yes, that is right. But give me a second, and I'll tell you what.